Capacitors are components that can store electrical pressure for long periods of time. When a capacitor has a difference in voltage between its two leads, it is said to be charged. A capacitor is charged by forcing a one-way DC current to flow through it for a short period of time. It can be discharged by letting an opposite direction current flow out of the capacitor. Consider for a moment the analogy of a water pipe that has a rubber diaphragm sealing off each side of the pipe as shown in figure 9. If the pipe had a plunger on one end, as shown in figure 9, and the plunger was pushed toward the diaphragm, the water in the pipe would force the rubber to stretch out until the force of the rubber pushing back on the water was equal to the force of the plunger. You could say the pipe is charged and ready to push the plunger back. In fact, if the plunger is released, it will move back to its original position. The pipe will then be discharged, or with no charge on the diaphragm. Capacitors act the same as the pipe in figure 9. When a voltage is placed on one lead with respect to the other lead, electrons are forced to pile up on one of the capacitor's plates until the voltage pushing back is equal to the voltage applied. The capacitor is then charged to the voltage. If the two leads of that capacitor are shorted, it would have the same effect as letting the plunger in figure 9 move freely. The capacitor would rapidly discharge, and the voltage across the two leads would become zero. What would happen if the plunger in figure 9 was wiggled in and out many times each second? The water in the pipe would be pushed by the diaphragm, then sucked back by the diaphragm. Since the movement of the water is back and forth, it is called an alternating current, or AC. The capacitor will therefore pass an alternating current with little resistance. When the push on the plunger was only toward the diaphragm, the water on the other end of the diaphragm moved just enough to charge the pipe. Just as the pipe blocked a direct push, a capacitor clocks direct current. An example of alternating current is the 60-cycle current produced when you plug something into a wall outlet. Capacitors. How are they made? There are many different types of capacitors used in electronics. Each type is made from different materials, and with different methods. Capacitors are also made to handle different amounts of electrical pressure, or voltage. Each capacitor is marked to show the maximum voltage that it can withstand without breaking down. All capacitors contain the same fundamental parts, which consist of two or more conductive plates, separated by a non-conductive material. The insulating material between the plates is called the dielectric. The basic elements necessary to build a capacitor are shown in figure 10. Perhaps the most common form of capacitor is constructed by tightly winding two foil metal plates that are separated by sheets of paper or plastic as shown in figure 11. By picking the correct insulating material, the value of capacitance can be increased greatly, but the maximum working voltage is usually lowered. For this reason, capacitors are normally identified by the type of material used as the insulator or dielectric. Consider the water pipe with the rubber diaphragm in the center of the pipe. The diaphragm is equivalent to the dielectric in a capacitor. If the rubber is made very soft, it will stretch out and hold a large amount of water, but it will break easily. If the rubber is made very stiff, it will not stretch far, but will be able to withstand higher pressure. The dielectric in a capacitor is the material that can withstand electrical pressure without appreciable conduction. When a voltage is applied to a capacitor, energy in the form of an electric charge is held by the dielectric. In the rubber diaphragm analogy, the rubber would stretch out and hold the water back. The energy was stored in the rubber. When the plunger is released, the rubber would release this energy and push the plunger back toward its original position. If there was no energy lost in the rubber diaphragm, all the energy would be recovered, and the plunger would return to its original position. The only perfect dielectric for a capacitor, in which no conduction occurs, and from which all the stored energy may be recovered, is a perfect vacuum. The dielectric constant is the ratio by which the capacitance is increased when another dielectric replaces a vacuum between two plates. Table 3 shows the dielectric constant of various materials. The variable capacitor. An additional screw is added to squeeze two insulated metal plates together and thus set the minimum amount of capacitance. The shape of the plates can be designed to achieve the proper amount of capacitance versus rotation for different applications. An additional screw is added to squeeze two insulated metal plates together and thus set the minimum amount of capacitance. The shape of the plates can be designed to achieve the proper amount of capacitance versus rotation for different applications. Capacitor values and markings. The older styles of capacitors were marked with colored dots or rings similar to resistors. In recent years, the advances in technology has made it easier to print the value, working voltage, tolerance, and temperature characteristics on the body of the capacitors. Certain capacitors use a dielectric that requires markings to ensure one lead is always kept at a higher voltage than the other lead. Figure 15 shows typical markings found on different types of capacitors. Table 4 gives the standard values used and the different methods for marking these values.